Good morning. Everybody's coming in all at the same time. Okay. Good morning. Wow, that was a flurry. Jessica, Allison, Brittany, Haley, Jessica again. Sarone. Okay. Seems like I saw somebody else. Ella. Yeah, Ella, Sylvia, Allison, Brittany, Haley, Jessica, Sarone. How you doing, guys? I can't see anybody, but let me see if I get everything on there. Yeah, there we go. There we go. How's everything going? Are you feeling like we're at the end of the last full week? Yeah. Okay. I've got a few things for us to do today, and then I'll talk about what I want the very last homework assignment, and it's one problem and one bonus. Okay, and it has to do with the springs. So that spring material for any of you who choose to take the final will not be included on the final. This homework that you have on the springs will be the only thing you have on springs. Okay, so and I'll finish up most of that today, and tie up any loose ends I've got on Monday, and then I'll have as soon as I get that homework in, which I should be Monday at class time. I should have everybody's averages done that Monday, and we can talk about that. Wednesday, I'm not going to do anything new, just questions, or I may even leave it for time for people to check in and ask about their particular situation in terms of homework and grade and so forth. Did you guys have any questions about that? A little different than what I usually do.
We don't have to take the final if our average is not enough, correct?
If you're happy with your average going in, if you chose to take a pass and you got a pass and you don't want to take the final, no, you don't have to take the final. If you opted for a grade and you got an A or a B or whatever you got, if you're happy with that, you don't have to take the final.
Okay, so
yeah, the reason
not taking the final will not affect us.
No, not at all. No, not at all. It's optional depending on your situation. So one of the reasons I'm even worrying about it is that there's some people who have a low test grade, and if they want the opportunity to replace that low test grade with a final exam, then I'll do that. Okay. So if you take the final and you make a higher grade on it than your lowest test grade, then I'll replace it with that and redo the average. Okay. So that's the reason. So no, it will not in any way penalize you or whatever. And you can have a copy of it. I don't know, just if you're stuck inside most of the summer, you can have some fun and do the DE final. Okay, whatever. Other questions, anybody?
And it will include everything we learned from the beginning of the semester,
yeah,
right? Or just
it's comprehensive, and it will go through what we did on the last test. So it's really going to be on the first two tests. But unlike the first two tests, it will be open book, open notes. Okay, so that's what it'll look like. It will not. If you happen to make lower than your lowest test grade, it just won't count. Okay, so it's not going to count against you in any way. It can only help you. And yes, it'll be from day 1 through what we had on the last test. Okay, springs will not be on there. Springs will not be on there. Okay.
We had a recording of what you taught us all semester.
I know. I was like, sorry about that. We got the last half recorded. I think it might send me to an early grave if I had to record the first half of the semester right now. I mean, it's a good way to go back and look at things and understand what you're trying to do and so forth, and that you can put me on repeat, which also means you're probably sick of seeing my face. But anyway, whatever. We're gonna I'll try to work with everybody to maximize the results in the end here. Other questions, anybody? Anything else? Okay, let me make sure I got everybody in, and I want to talk a little more about springs today, because actually what we've talked about is the sort of not realistic part of springs, where you've got these undamped things, these things that are just free motion, which really are just not very useful because they happen in the only place they really happen would be in a vacuum. All right, so let me share what we got, and then we'll look at this. All right. So there we go. All right. So in doing this, I'll remind you of some things we did Wednesday, and then as far as what I usually get done in this course, I usually dip into one more chapter on something called Laplace transforms. I think we did really good to get where we got to. Many DE courses do not include Laplace transforms, but it's something I like to do for various reasons. It has to do with it has to do with computing time, actually. In a Laplace transform, if you can transform a DE into some kind of algebraic equation, which is what Laplace transforms do, you can cut down computing time significantly on problems you want to do numerically or on the computer, which is interesting. I had a student do an independent study one time, and she actually measured computing time for the computer to do it by the DE method and then by the Laplace transform method, and she showed a clear difference between the two. But that be that as it may, we've done a lot, and I'm really happy with where we got to. Okay, so what I want to look at today is the sort of more realistic case where we're going to look at free damped motion. Okay, so what we looked at yesterday, we got graphs that had an amplitude, and the spring just went up and down and up and down and never slowed down. It just does the same thing over and over again. That's not very realistic. Again, as I said, unless you're in a vacuum. Typically, there's going to be some kind of resistance offered to the spring besides the resistance that's offered by the spring constant. And it's usually by some surrounding medium. For instance, if a spring is operating in the air, it's going to have some air resistance. If the spring happens to be operating for some reason underwater, it's going to have a resistance there. Springs or whatever, maybe you've got in an oil pumping situation, you have a spring and how you're pumping it, then you have to consider how much resistance the oil gave to the system. And all these forces, guys, are called damping forces. All right, so the air could be a damping force, the water could be a damping force, and whatever. But it's been shown physically that these damping forces, damping just means sort of a tamping down of what the spring's going to do. It eventually slows it down, or it slows it down in some sense. Turns out that they are proportional to a power of the instantaneous velocity. Now, remember that what we're looking for in these problems is an equation of motion, so x of t. If I looked at x prime of t, if x of t is an equation of motion, then x prime of t is going to be its velocity. X double prime of t would have something to do with acceleration and so forth. But dx dt is what gets added here. For us, so we can have an equation we can solve, we're going to use something really simple, and that is just this constant that is going to provide the thing that's proportional to the instantaneous velocity. So in for air in physics, that constant's usually 1. In hydrodynamics or something, when you're dealing with water, that constant's usually 2. Now, we'll talk about how we work this into the problem right now. Either somebody just disappeared or whatever. Let's see. All right. Okay, so let's recall again what we did yesterday, because we're just going to add on to this model we did yesterday. What we did yesterday was talk about what happened in a system where you had a spring with a spring constant K, all right? And also working on this spring would be gravity. So we started out with this force equal mass times acceleration. That's working in one direction, and the spring constant over here on the other side is working in the other direction. What we did was we moved that kx over right here, and we solved a dE. That's what we were doing on Wednesday, okay? So all we had working in this system was essentially gravity and the spring constant. And we talked about how to find the spring constant and so forth. We'll be doing some more of that today. What we're going to add now is just another element to the system. And this other element I'm going to denote by minus beta dx dt. Now notice, there's that derivative I was talking about, that x prime. Beta is going to be positive, and beta is something we call the damping coefficient, all right, or the damping constant. It's given a negative, it's given a negative, well, this whole term is negative. Beta is positive. Dx dt is the rate of change there, or the instantaneous velocity. The term's less than 0, as it's gonna act in a direction opposite the motion. It's keeping the motion tamped down, okay? So we end up with an equation that has another term on the right-hand side, all right? So here's force equal mass times acceleration. On the other side, we've got these other things working in the opposite direction, these damping constant, damping coefficient, or damping term, we'll call it, and then the spring constant term. Okay, so actually, then what we end up with is a second order dE. If we can figure out all these things, we've got a second order dE with a term for the second derivative, a term for the first derivative, and a term for just x. Yesterday, this middle term was not in there, all right? We did not have this damping coefficient yesterday. So yesterday, we were just getting things that went up and down and up and down and up and down and never did anything different. What we might expect a spring in reality to do is maybe go up, it's being damped by some force every time it comes back, but eventually it just kind of peters out there. Okay, so this is what's going to happen, or one of the things that can happen when you have these damping coefficients. Okay, so got a second order linear dE with constant coefficients, which we spent most of chapter 4 trying to do. The K was the spring constant, M was mass, and this beta is our new damping coefficient. All right, so let's talk about how we're going to solve this. Now, the first thing I'm going to do, let's go back to where it was. The first thing I'm going to do here is divide through by m, okay? And then I'm going to start to make some assignments to these variables here. When we set up the equation, this is what we're going to look for. We're going to look for them to tell me what beta is, what m is, what the spring constant is, or what can we find the spring constant, and so forth. Now, in reality, when we solve this one, and this is the way it goes a lot of times in physics, they will actually sort of make I shouldn't refer to them, mathematicians do it as well, but whoever's solving the problem replaces different things with some other term, okay? Which in this case, what we're going to do is say, well, we're going to refer to this beta over m from now as 2 lambda. And you might say, well, why not just lambda? It turns out that if I let it be 2 lambda, something really nice happens with the thing when I solve the characteristic equation. In other words, what they say in the book, it makes it algebraically convenient, okay? In other words, if we have to use a quadratic formula on it, by letting this thing be 2 lambda, maybe we just have something that comes out very nicely and we don't have to worry about a denominator in the root or something like that. But that's what we're doing. We did this yesterday also, where we said we were going to call k over m omega squared. And that omega came out, if you remember, in the form, when we had amplitude, it came out in the form sine omega t, or c1 sine omega t plus c2 cosine omega t, something like that, okay? So that omega, by letting that be omega squared, that omega had to do with the spring constant and the mass together, all right? So we're going to keep that in mind, and I'll show you why it makes a difference in a little bit. Questions, anybody? Okay, so we've got second order constant coefficient, or second order dE with constant coefficients. If I look at what I did with my substitutions back here, all right, what you've got is a a characteristic equation that would look like, now guys, again, I flirt back and forth with this. I usually put M for my characteristic equations, but because M is standing for mass here, I'm just putting R here. So I'm writing a characteristic equation. That's gonna be R squared. Coefficient on R, that first derivative, is gonna be 2 lambda. And then K over M, we assigned omega squared to that. So here's our characteristic equation. Now, the whole thrust of this lecture, guys, is that that's a quadratic. There are 3 things that can happen with a quadratic. Somebody tell me what, in terms of roots, we've done this before in a different context, what kind of potential roots can you have when you solve a quadratic equation? Somebody unmic, or anybody unmic, and tell me what kind of roots you could possibly have with a quadratic, if you're solving a quadratic. And that's all you're doing here, guys. What kind of roots can you have?
Repeated.
You can have repeated roots. Good. That's one. What other kind of roots can you have? Those of you in complex should know something about this. What other kind of roots can you have?
Real.
You can have real roots. You can have real distinct roots. And then sort of the default, the last thing is, if the roots are not real, then they're going to be roots that we get a square root of a negative under the radical when we do the quadratic equation. Those are going to be complex roots. And we've learned how to write solutions. This is why I like this application so much, because it does sort of everything we've learned how to do in chapter 4. We've learned how to write solutions for all those things. We've learned how to write solutions when there's a repeated root. We've learned how to write solutions when they're distinct real roots. There would be 2 of them because it's order 2, okay? And we have learned how to write things with imaginary roots. And here's where all this comes in terms of solving the characteristic equation. This thing, of course, right here, the coefficient on R squared is 1. The coefficient on R is 2 lambda based on that substitution that I made. And this is omega squared. Remember that the 2 lambda had to do with the damping forces and the omega had to do with the spring constant. That's going to be important to us later. What happens when we solve it is we're going to be minus b would be minus 2 lambda plus or minus the square root of this b squared, which is 2 lambda squared, minus 4ac, which in this case is 4 times 1 times omega squared all over 2. When I play that out, I can divide that 2 into that minus 2 there, and that's how I get the minus lambda. This thing right here, I see a 4 in both of them. When I see a 4 in both of them, the square root of 4 is 2, and I could take that 2 out, and I'll just have lambda squared minus omega squared there. That's why we did these funky substitutions here, this 2 lambda and ultimately omega squared, because now our roots look really nice in terms of those things. I don't have this a fraction to deal with down here. I've just got this. And furthermore, the roots are determined by what happens underneath here. If that thing is 0, we're going to have a repeated root. If that thing is negative, we're going to have non-real imaginary roots. If that thing is positive, we're going to have 2 distinct real roots. So that's why we made that substitution. Okay. So what we're going to do is see what happens to this D depending on those 3 cases. Okay. So let's look at maybe the easiest one first. In case 1, we're going to assume that what's under here is positive. If what's under here is positive, remember that's called the discriminant. Okay. It discriminates between the kind of roots that we have. And the 2 distinct real roots are going to be this minus lambda plus that, and then minus lambda minus that. Okay. So there they are. I called them R1 and R2 here versus M1 and M2. Okay, but same thing. They're the roots of the thing. Well, if I look at then they're the roots of the characteristic equation. And if you look at what this thing says here, we've got this lambda squared minus omega squared. Omega squared was K over M, and that lambda was the beta, or 2 lambda was beta over M. what this says is that this lambda term is the term concerning beta, or the damping, and this omega term is the one concerning the spring constant. Beta, if this is going to be positive, beta has got to be large relative to the spring constant. All right. So in other words, the damping is going to have more of an effect in a sense than it's going to sort of overpower the spring constant. And when beta is large when compared to K, the situation is called overdamped. Okay. I haven't looked at a physics book lately, but I'm not sure how far they go into the springs in an introductory physics book. I don't know how. You probably just went into simple harmonic motion. I'm not sure. Haley, you've had physics. What have y'all done with springs? Haley, still there? Unmic and talk to me if you're still there, Haley. Anybody else had physics that you talked about springs in a damping situation? I kind of think they may not do that in intro physics, but anyway. So anyway, if the beta is large compared to the spring constant, it's called overdamped, and that's when we have two distinct roots. All right, let's see what happens. If we have two distinct roots, we know how to write the solution. We write the solution like that. We say C1e to one of the roots, so minus lambda plus that t, plus C2e to one of the other roots, minus lambda minus that t. That's what our solution looks like. So if in the beginning of a problem, you can identify lambda and omega, you've got your solution, you've got it there. And then of course the e to the minus lambda t right here, that's what we would end up with if we just factored this term out right here, e to the minus lambda, and then just left these two right there. Okay, that's not an indication of complex roots. It's just an indication that you've got e to this minus lambda, which is a real number. So there it is right there. That's the solution. We know how to do that. I want to see what happens in this solution though when I look at an overdamped situation. If I look at this thing right here, remember lambda was positive. If I let t go to infinity, this e drops down into the denominator. This e drops down as an e lambda t. And if t gets bigger and bigger, e to a positive power gets bigger and bigger. That's a t right there, guys. E to a positive power gets bigger and bigger. That means the motion, or the x of t, the position at any time, is going to do what? If I drop this down and my denominator gets bigger and bigger, what's going to happen to this thing right here, the whole thing? What's the position going to go towards? X of t is going to go towards 0 there. Okay, now remember x of t is the position of the spring at any time t. So again, the bigger t gets, all right, what's going to happen is that this drops down and it causes the whole thing to get smaller. What we get, and I'll show you this in a specific example in a second, but what we get there is this, first of all, we get this non-oscillatory motion. We don't have the sines and cosines that make it go up and down and up and down. It is not, in a sense, it's not oscillating, all right? And in another sense, it's getting, if the damping factor is bigger than the spring constant, is having more of an effect on what the spring does. It might look like this. You might have started it up here. In other words, that means below equilibrium, and let it go, and then it just sort of wandered on down to the position, to stopping. Okay, essentially right there. It might, in this particular case, you might again start below equilibrium here and give it a push. Maybe you gave it a hard enough push in terms of the velocity of the thing so that it went through equilibrium once, but then it just came back up and it never did anything else. It just sort of started stopping, basically. Okay, so let's look at a problem and see what happens and see what the graph looks like. All right, so suppose a spring has constant equal to 4. So as I'm reading through the problem, and there's k equal 4, and it has a 32-pound weight suspended from it. Okay, so we know that weight is bound up with this idea of weight equal mass times gravity here, right? So the weight is 32. I need to know the mass. Since we're talking about feet and feet per second and so forth, then this is going to be 32. G is going to be in 32. That means M is equal to 1. Now I'm finding all these things so I can set up my equation of motion. And once I get it set up, it's not hard to solve. The next thing that it tells me, and I'll look at this carefully, guys, because this makes a big difference when you do your problem. It says the mass is released from a position 1 foot below equilibrium. Now, remember, below equilibrium means you're pulling the spring down and making it longer. So basically that's saying that its position at time 0 is positive. It's pulled out, it's positive. It shows up on the graph as the 0.01 or whatever, okay? But that's what it looks like. So if it says below equilibrium, x of 0 is equal to 1. There's a really good set of problems in the spring problems in this section, and they're 17 through 20, and they make you look at a graph and they say, was that below equilibrium or above equilibrium? So you could get used to this sort of disconnect between what it looks like and what you're saying below, and you're graphing it above, okay? The next thing says that it's released with a downward velocity of 1 foot per second. So if it's a downward velocity, it's working with gravity, so x prime of 0 is also 1. So those are my two initial conditions. So that's what that second sentence is giving you, all right? Actually, yeah, right there. The mass is released there and with a downward velocity up there. So that's giving you your initial conditions. The next thing is the thing we did not deal with yesterday. The medium it is in offers a resistance to the motion that is numerically equal to 5 times the instantaneous velocity. So that says beta is 5. All right, beta is 5. Sometimes it'll say numerically equal to instantaneous velocity when it'll be 1. Sometimes it'll be √2. Anyway, it's some constant times dx dt or x prime. Okay. Now, one other thing we know is that we called that 2 lambda. What we called 2 lambda was beta over m. Our m is 1 here, so our 2 lambda is 5. That makes lambda equal to 5/2. Now this is where all that substitution stuff comes in. K over m was 4 over 1, so that was my omega squared. Now here's what I want you to notice here. If I square 2.5, it's bigger than omega squared. In other words, lambda squared is bigger, okay? So I wind up with something that's greater than 0. Right? Wind up with something that's greater than 0. So that means it's overdamped. All right, let's go back and look at the equation. The equation looks like this: x double prime plus 2 lambda, that was my beta over m, that's 5. Omega squared, that was my k over m, so that's 4, plus 4x equals 0. There's my equation. Just identify your k, your beta, your omega, whatever. You can do all of that and you can find it very easily. Okay. When I solve that, is the characteristic equation. Now here, see, I went back to m. The characteristic equation looks like m squared plus 5m plus 4. When I factor, I get m equal -1 and m equal -4. I know what a solution looks like to that. It just looks like that. If I've got real roots, it's c1 e to the minus t plus c2 e to the minus 4t. So this is something that would have been easy to do based on the last test. 2 distinct real roots look like that. The only thing I've got left to do is find C1 and C2. All I did there, guys, I knew that x of 0 was 1. So I put in 0 to this one. There's x of t. Where'd it go? X of 0 is equal to 1. Because of all those e's to powers, you get a lot of 1s in there. All right, so you get C1 plus C2 is -1. I then took the derivative of x of t. Our initial condition there was that x prime of 0 was equal to 1. I took the derivative, I put in 0, I set it equal to 1. I solved those two things together, solved those two equations right there together, and found my C's. So we've been doing that all semester, guys. Okay, just put your initial conditions in. I wind up with these two things right here. C2 was 2, C1 was 5/3, and C2 was minus 2/3. Well, that looks kind of fuzzy. C2 from right there was minus 2/3. Okay. When I put them on the equation, there's my equation. It was C1, so 5/3 e to the minus t minus the 2/3 e to the minus 4t. That's the equation of motion. So it's really just a matter of, in this one at least, it's just a matter of figuring out what K and M and beta and all of those things are and solving your equation. Now, here's what I want to look at on this one. I ask a couple of questions. Will it, before I even look at the graph, will it pass through equilibrium? Well, equilibrium is where x of t is equal to 0. So the reason I set it equal to 0 is because at equilibrium, we're crossing over that place where it would be in balance, right before I set it in motion. So if I try to solve this, I'll move all these things over. I multiplied through by 3. I then divided by 5 and multiplied by e to the 4t. I ended up with t equal natural log of 2/5 over 3. Now, I put that in the calculator, guys, but you can see right away that thing right there, since the thing you're taking the log of is less than 1, you're going to get a negative number. And so that's of no use to me. I'm only interested in this equation of motion when time starts at 0. So this is telling me that's the only place, if that's the only place it goes through equilibrium, that's behind where I'm interested in. I'm interested starting from t equals 0. So it does not pass through equilibrium. So something is keep tamping it down, and it's those damping forces. All right, I want to do one other thing. Suppose I wanted to find its extreme displacement. If I wanted to find its extreme displacement, guys, I remember what I need to do to find extreme displacement. It's like a high point or a low point. I need to find the derivative of the equation of motion. So this thing right here that I found was x prime of t. So there was x of t. If I take the derivative of that thing right there, it'll be minus 5/3 e to the minus t. Multiply by the minus 4 here, you're going to get 8/3 e to the minus 4t. If I do the same thing with that one, solve for t, I get, well, it does there is a time where it has its maximum displacement at time 0.16. So in that case, we know it does not, and that it seems that is the only spot. Right? That's the only spot where we have this the furthest away, either a local max or a local min. Okay, if we were looking at the graph. Okay, so guys, I've got all this stuff on the on my calculator here on the computer. So I'm going to shift over to that. So bear with me for a second. And well, I've got all these things up in here, so I want to use them to show you what the graphs look like. And if I ask you to do a graph, which I did on those couple of homework problems I'm giving you, you can use your computer to get the graph. Okay? Let's see if I can get it up. All right, somebody give me a yay if you can see it. Everybody okay? Can everybody see it? Can anybody see it yet?
Yeah.
Okay, good. All right, thank you. All right, so guys, I've entered this first one right here. The equation of motion was 5/3 e to the minus x minus 2/3 e to the minus 4x. Again, I'm dealing with x and y instead of t and x, but you'll get the same picture here. I don't have a way to get that t variable in there. So I'm going to graph this one. I think I set the window where I wanted it. Yeah, I think I've got it. Let me graph it. Okay, there's what it looks like. Okay, notice here that we said at time 0, it was at a position of 1. That's what I see. Now remember, this was, if it graphs up here, this means it's below equilibrium. It's been pulled down. It looks like it rises up a little bit and then starts to come down, and then it never crosses the axis. You don't remember how the only place it crossed the axis was back here at a negative? That's that indication right there. It never does that. It just gets, theoretically, it gets closer and closer to a position of 0. Of course, we know it eventually stops. But if I traced this thing, let's look at it. If I trace it and see if that's kind of verified with what I was looking at. Let me go back to where it crossed this axis back here. That was around minus 0.31. I think we got minus 0.30. Okay, we weren't interested in it because I'm not interested in that negative time there. If I go right here, we see that can't get it right on there, but it's right on 1 there. Now, let's see if we can see that it appears to go up a little before I find that extreme displacement, and maybe a little further up. Okay, back here, I was at 0.13, about 0.14. I go here about 0.17. We had said it was at about 0.16. Okay, so it goes up, it reaches its only spot of actually local max in this case, or actually a maximum in this case. I mean, an absolute min. An absolute max, and then it starts going down. Okay, so that's what this damped motion looks like. That's what the damped motion looks like. Okay. All right, any questions about that? Are we okay on that? All right, I want to get out of this one and go back and share with, get my screen back if I can. Okay, let's do it again. And should come up, hopefully. There we go. Okay. Yeah, right as the semester ends, I finally got hold of all my technology here. Okay, so that's what happens in that over-damped situation. All right, now, let's look at another one. Let's look at another problem. This is a similar problem. It says a 16-pound weight is attached to a 5-foot-long spring. At equilibrium, the spring measures 8.2 feet. They're giving you information there that's going to allow you to find the spring constant. Because if you remember, the spring constant in this one was equal to, remember, let's look at this. I don't think I wrote it down, but force was equal to Ks. My force is the 16-pound weight. My, it says, is attached to a 5-foot-long spring. At equilibrium, the spring measures 8.2 feet. So you attach it, it goes down 3 feet. All right. So this is K. That's 3. Actually, that's 3.2. Sorry, it goes down 3.2. There it is right there. Okay, so that's 3.2. They didn't give it to you right away here, but they said if you put it on there, this is how far it goes. And the distance between 8.2 and 5 is the 3.2 that you're looking at. Okay, so if I divide 16 by 3.2, I get K is 5. All right. Remember, omega squared is K over the mass. Well, the mass in this case is going to be, it's 16 pounds. The weight 16 pounds is the mass times the 32, which of course is gravity. So mass in this case is 1/2. So K over M is K over half. That's equal to 10. That's what goes in that spot. Remember, that was the K over M, or the omega squared. All right, that's where that goes in the equation. What goes in the other spot was the beta over M. And the beta over M here, if we keep reading, it says, the last sentence says, if the surrounding medium offers a resistance equal to 1 times the instantaneous velocity, find the equation of motion. So there's beta. That is beta over M is 2. That's where that 1 is. That's the 1 that's right there. And the mass is right there. And that's the 2 that goes there. Okay. And when we, for our algebraic convenience, that was our 2 lambda. Okay. And then we had x double prime. So again, guys, this one right here is the beta over M. This one right here is the K over M. Now, if we wanted to suck lambda and omega out of that and look and see what was happening with lambda squared minus omega squared here, we would see that we get something less than 0. Okay, so if 2 lambdas, 2 lambdas 1, so 1 squared. This omega squared was 10. All right, so we'll get a -9 under the root right there. That says this thing is what we call underdamped, because the spring part of it, the lambda part of it, the spring part of it here is bigger than the damping forces right here, and it gives me a negative under the radical when I solve it. You'll see me when I solve it in just a second. So if you want to know what kind of problem it is right away, compute lambda squared minus omega squared, or you could just set up your equation and see what happens. So my lambda would be 1, my omega squared would be 10, so lambda squared minus omega squared is less than 0. That says that I've got complex roots, and it's what we call underdamped. Spring constant is having more of an effect than the damping coefficient. Okay, so here's the equation. Now, one thing I didn't pick up yet was the initial conditions. So let's do that and make sure everybody understands how the initial conditions work. We'll go back to the initial conditions. It says the weight is pushed up and released from rest at a point 2 feet above equilibrium. Now, remember, if it's above equilibrium, this thing's being released from 2 feet above, you're pushing the spring up. It's kind of making it shorter. That's how I remember that it's negative. It's right here. So that says the position at time 0 is -2. And that, again, is because it's released from a point above equilibrium. It's exactly opposite from what you think. And then it says released from rest. That means you don't give it a push up, you don't give it a push down, you just let it go. And if you just let it go, you have the initial velocity of 0. So that's where, if it says release from rest, that's going to be your condition right there. Okay. All right, let's look at that one. There's my characteristic equation. I'm going to solve it using the quadratic formula. I wind up with -2 plus or minus square root of 2 squared minus 4ac, which is the 1 times the 10. Notice what we said was going to happen. We get a negative under that radical right there, which means I'm going to have 2 roots, these complex roots. You guys know how to write that. All right. The way you write that is going to be the imaginary part right here, or the real part, the -1, is going to be a coefficient on the e to the minus t thing. Okay. That 3 right there, that's the coefficient on I, gets put in here with the sine 3t, cosine 3t. So that's the solution. All right, that's the solution. Now, again, I need to find C1 and C2 based on where it was released and what kind of push it got when it got released. Let's slow up a little bit here. This gets kind of messy. You can check it later, but all I did, I knew that, let me write down what the acute conditions were down here. I got x of 0 is -2. X of 0 is -2. And x prime of 0 was 0, since it was released from rest. All right, now, if I go to my x of t, and I put in 0 here to figure out what the relationship is there. If I plug in 0 here, e to the 0 is just going to be 1. That sign is going to drop out. The cosine of 0 is going to be 1. So I'm going to get C1 equal -2. So that one was easy. Okay, I got C1 is -2. I then had to take the derivative in order to use that condition. The derivative was kind of messy, but it's not terrible because of things you're doing here. If you're letting t be 0, everything that's got a sign in it's going to drop out. everything that's got a cosine in it's going to be 1. So when I go through that process there, guys, and that, again, that's just the derivative of my x of t. I had to use the product rule on that thing. That's why it looks so long. I wind up with 0 equal, putting all those zeros in, I wind up with this, 3c2 minus c1. Since I knew c2 was minus 2, I can just put that in here, move it over, and I've got my c2. All right, so the mess in there is just figuring out what c1 and c2 are. Okay, let's see what we've got. Here's my equation of motion. Okay. So that looks a lot like the kind of that I had yesterday, except it's got this e to the minus t thing on it. What I said yesterday was that this was not a very convenient form. And we're going to do the same thing with it today that we did yesterday. We're going to put it in something called amplitude form. It's going to work virtually the same. So I'm just going to remind you of what we did yesterday. What we did yesterday is if we put it in this form with an amplitude out there. Now, yesterday it didn't have this e term in it. The amplitude just told me how high it rose and how low it went down, and it kept doing the same thing. Now, this e is going to have an effect on that, but it looks exactly like that form. It looks like the sine of, now the coefficient here, remember how we got the 3? It was just under the radical there. It was on the root there, all right? So it'll be omega squared minus lambda squared. And there's the t. The thing that we had the most trouble finding was this phase angle right here. It's what causes a shift in a trig function. So I'm going to go through that process one more time and to tell you how we find the phase angle so we can put it in amplitude form. These 2 problems that I gave you, the one that's for credit is one of the first type that's pretty easy. It doesn't have the e term in it, but I want you to put it in amplitude form for me, and it works the same way as what I'm going to do again today. The second problem is one like this, and it's a bonus problem. Okay. All right, so what we decided yesterday, when we made all those substitutions, we decided if we let a be the square root of c1 squared plus c2 squared, and tangent of phi ended up being c1 over c2. Okay, now let's see what my c1 and my c2 here are. My c1 is minus 2. There's that one. My c2 is minus 2/3. Now, the way we got this tangent right here was saying sine over cosine. So the c1 had to do with a sine, and the c2 had to be with a cosine. Both of them are negative. What quadrant do I have to be in if both my sine and my cosine are negative here? And that's important to find in this angle. What quadrant do I have to be in? Both sine and cosine are negative. Before I go jumping off on this stuff. What quadrant, guys? Somebody might tell me. Sine negative, cosine negative.
The third?
The third, exactly. You're in the third quadrant. So that's going to help me in just a second. So what I want to do is find this a. This a is the same as it was yesterday. It's the square root of the c1 squared and the c2 squared. And when I do that, I get 2 root 10 over 3. So that's my a. So that's done. I'll put it in a minute. As far as this omega squared minus lambda squared, is simply going to be that thing that was, it's still going to be 3, the same as it was before in that other thing. So this thing right here is, it actually, where it comes from is this, guys, where you got the square root of minus 9 under that when you were doing the quadratic back there. That was a 3i. This is 3. This is going to be 3 right here. All right. It's this thing we have to find. So let's dip off into a little bit of the trig for a minute. We said that the tangent was C1 over C2. C1 over C2, okay? got that. Yeah, C1 over C2. What I wind up with here is the invert and multiply, and I'll get 3. Tangent's positive, but we just noted since both of these things were negative, that we were in the third quadrant. Okay. So because we're in the third quadrant, check something for a minute here. Because we're in the third quadrant here, we know that when we do this on the calculator and we get 1.249, we're just getting a reference angle for an angle that should be in the third quadrant. So there's a reference angle. I'll get the angle itself by adding pi. And that's how I got 4.39. It was pi, this distance, plus the distance of the reference angle, 1.249. And I get a 4.39 for the phase angle. Okay. All right. So here it is right here. That was my A. Square root of C1 squared plus C2 squared. The sine of the angle in the original was the same, that's 3, and then we do the phase angle based on what C1 and C2 are. Okay, so let's ask ourselves for a minute what we expect. Look at that e to the minus t term. If that weren't in there, this would just be the amplitude, that would be the sine, it would keep going up and down and up and down. If I drop this down into the denominator, I'm going to be dividing by e to the t. Now, the sine is just going up and down, so it's never going to get any higher than whatever that amplitude is. But because I'm now dividing by e to the t, the denominator is getting bigger and bigger. I'm expecting the position to damp this thing. So let's look at what the graph of that looks like. Question before I go to the grapher again. All right, let's see if it looks like what we think it ought to look like. Let's see here. Let's get that up. All right, can you see it? Has everybody got it before I start talking about it? Does everybody see it? Anybody? Yay, nay?
Yes.
Okay, good. All right, so I'm gonna go back to my y equal. I don't want to do this one anymore. Let's get it off for a second. So I'm gonna get it off. I'm gonna look at this one I just did. It was 2 root 10 over 3, e to the minus t, or x here, sine of 3x plus 4.39. I think my window will still hold, so let's look at the graph. Whoops, I forgot to turn it on. Hang on. I'll go down here. All right, let's go back and turn it on here. All right, there we go. Okay, that's more realistic about what you expect to happen. Notice here that we've got this thing down here, 0 minus 2. Its position at time 0 is minus 2, and that guys is above equilibrium and headed upward. I could find the first place here if I wanted to. I could find the first place where it reached this max. I could find the next place right here. I'll look at that when I come back to it. But this is kind of what you expect here to be happening. I'm gonna play with it for a minute, guys. I'm gonna do a zoom box on it for a second, and let's see. And that allows me, I'm gonna move this box back a little. Let's see, I'm gonna go back that way and just sort of pick up some things and do a box around it and extend it a little bit. Let's see. Okay, and then go, well, I need to enter it before I do that, sorry. Okay, there we go. So I'm gonna roll it up, make a box, roll it out, like that, so I can kind of see what's going on there. Probably should have made it a little wider, but anyway, enter and see what I see. I can see a little more what it's doing there. I mean, it's definitely doing that, but if I make a bigger box, I can see it's just getting tighter and tighter on the axis here. All right, in other words, the position is going to 0. It's petering out. It's got this damping force on it that's causing it to do that. Okay, questions about that, anybody? Okay, let's go back to the other box here. Okay. Share the other screen. Okay, that's all right. There we go. So guys, let me say one thing about this. If I wanted to find out where this thing had its maximum height and maximum min, I would take the derivative here and set it equal to 0. If I wanted to find out where it went through equilibrium, that's probably the only thing I asked, but if I wanted to find out where it went through equilibrium, that would mean I'd want to find out where this was 0. Well, where is the sign equal to 0? If you think about the sign being 0, this angle right here, 3t plus 4.39, would have to be some multiple of pi. So if you let n be 1, if you let n be 0, this will be negative, so you don't want that one. If you let n be 1, pi minus 4.39 will also be negative. If you let n be 2, you'll find out where it goes across the axis. You just look at what the sign's doing. If you want this thing to be 0, that's got to be a multiple of pi. Okay. All right. One other situation, and we'll be done here. So we only had one more case left, guys, and that case was, what do we expect of the graph when we have repeated roots? When we have repeated roots. When we have repeated roots, this is probably the easiest case, although it's the case which is sort of important. This case is called critically damped. And remember, when we have repeated roots, we would have a 0 discriminant, or we'd have a 0 under that radical in the quadratic. If this is 0, that means those two things are equal. Okay? Now, that's why it's called critically damped, because any slight change in the one that deals with the damping forces, or any slight change in the spring constant, is going to cause it to bump one way or the other. It might be underdamped or overdamped, depending on how you adjust these things. But if they're exactly equal, it's called critically damped. All right. So let's look and see what happens in one of those, and then we'll call it quits here. Going through the problem again, just setting it up. 4-foot spring measures 8 feet long after a mass of 8 pounds is attached. All right. So that says 4-foot spring has gotten stretched 4 feet. So that's my S, my K. The weight on the other end of it is 8. So I get K equal 2. So there's my spring constant. Okay. My beta, look at this one. It says the medium through which the mass moves offers a damping force numerically equal to √2 times the instantaneous velocity. There's my beta. Okay. I can find my mass by knowing that we had a weight of 8 pounds here, and we're dealing in English metrics, or English. We got 32, which is gravity. I wind up then with m equal 1/4. The omega squared, of course, is going to be k over m. So that's 8. So I've got my equation. There's 8. Beta over m is √2 over 1/4. There's that one. And I wind up with this thing right here. Now, as far as my initial conditions go, it says find the time at which the mass attains its extreme displacement from equilibrium, and find the position. Oh, here it is. Sorry, I read too far. It's released from equilibrium position with a downward velocity of 5 feet per second. So x prime of 0 is 5. It's downward, it's working with gravity, so I get 5. And what else did it tell me? It said, I'm looking at what I got here. Oh, here we go. The medium through which the mass moves offers a damping force. Find the equation of motion if the mass is initially released from equilibrium position. Now, it says initially released. It says, it doesn't tell me, I just let it go. So I'm looking at another one of these x of 0 equals 0 here, I believe. Get down to here. So there's my characteristic equation. If I solve it, I get a repeated root of -2 root 2, and there's my quadratic equation. This thing turns out to be 0 under here. I get -2 root 2. So that's what my solution looks like with repeated roots. What's it look like, guys? It puts the root on it, C1e to the -2 root 2t, and then puts another t with it again. So we know how to do that. I took my derivative here, plugged in my initial conditions. There were my initial conditions. I found out that C1 had to be 0. And then if you took the derivative and put in 5 and 0, you find out that C2 has to be 5. Okay, so just typical initial condition stuff. When I put those C1 and C2s on there, if C1 is 0, this piece drops out. All right, C2 is 5, what I get is this thing right here. Now, my question here then is, does it pass through equilibrium? Well, the answer here would be, yeah, I think it passes through equilibrium because there's a place where it's 0. The E part of it's clearly never 0. The 5's never 0, but it certainly can be 0 when time is 0. I expect this thing to be at equilibrium at time 0. Okay. If I want to look at extreme displacement, in other words, what's the highest that it rose, or the time when it rose that high, and then you could plug it into the equation to find out what the position was. But you're going to take the derivative of this, which requires a product rule, which is what I did right here. So first times root of the second times root of the first, and then pull out the e to the -2 root 2t. I'm left with this. Remember, this is the derivative. You find critical numbers by setting this thing equal to 0. That e part's not going to be 0. This part's going to be 0. When I solve for t, I get 0.354 seconds. 0.354 seconds. Okay. So, so I'm going to go back and look at the picture of this one and see if it holds up and see what it does. And then guys, I have it on here, but I've got it on Moodle. The two problems, you'll see, I've typed them out. I've put them on there. The first one is for credit, and the last one is for a bonus. The last one is this last stuff that I did. I got one more thing to talk about. That's force motion. I'm not going to do that. I'm going to finish that up on Monday. But I'd like this homework, before I look finally at the graph of this thing, I'd like this homework Monday. I've got to have it Monday by class time, because I really need to get it graded so I can let everybody know what they need to be planning for. Okay, so Monday at class time, I'll have all your averages done and so forth. Okay, let's go to the grapher on this one and look at what it looks like finally. Yep, there we go. Okay. Screen, let's resume share. Somebody tell me when you can see that. Something looks weird to me. It's not sharing the way I want it to. There we go. Let's try again. This one. Okay. All right, good. All right, I'm gonna go down to the third one here. Let's see, let's cut that one off. Let's go down to this one, which is what we saw, how we solved this in this critically damped situation. And enter that and graph it. So that, whoops, I didn't change my window back to what I wanted it to be. Let's go from -1 to 4, 1, and let's do -3 on that. And let's just do 2 on that. All right, let's see what the graph looks like now. Okay, there we go. Notice what we said, it went through equilibrium once, basically that's when it started. This extreme displacement right here, if I look at the trace, I think we said it was about 0.35. So if I trace over there to see if I'm right there, yep, about 3.2, 3.25. If you want to know how high it was or what its position was at that time, you'd plug in this value. But I mean, of course, the graph just gives it to you. It's at 0.6 feet, I guess, is how we were measuring things there. And the time it reached there was around 0.3. We solved it exactly. It was 0.35, I think. Okay. Okay, guys. So you got one thing to do. Again, this spring stuff will not be on the comprehensive final for those of you who choose to take it. The only time we're getting quote tested on it is with this this last homework problem and the bonus problem. So we've got right now, I think we've got about close to 140 homework points, which is good, because the more you have, the better it is in terms of things you might have missed, all right, which will be a lesser percentage of the whole. But there's another chance here to get a few bonus points, and there are parts to these questions, so you can get some of the bonus and maybe not get all of it particularly. And then the first problem is for credit. Questions, anybody, before we sign off today? All right, I hope you have a good weekend. If you have any questions, just email me, and I will, I'm trying to think if there's anything I've forgotten to tell you. I'll get back in touch with you. If anybody has any personal questions or particular questions for your situation, just email me. I think I've got for everybody that handed it in, I've got all the homework back. So if you're missing a homework, let me know. I'll look for it, but I think I got everything that got sent to me back. Questions, anybody? All right, while you're looking at that nice graph, I'm gonna take off. I will see you on Monday morning. Have a good weekend.
You too.
Thank you.
Have a good
Bye-bye.
weekend.